My name is Scott Halverson. I'm a solutions architect along with Vineeth on NVIDIA's supercomputing team. And we work closely with a variety of DOE labs. Basically we're the customer-facing engineers that you guys work with. And so today I'm going to talk about something that is relatively new in the CUDA world. This is CUDA tile, or CUTile in the context of Python at least. And I'm going to talk to you a little bit about what it is, what we're trying to accomplish, and how you can get started with it. Okay, so let's see. So to start off, what are we trying to accomplish? This is the agenda that I want to cover, but basically the overall goal here is to explain why we want a new programming model and why this is beneficial. So I'm going to introduce CUDA tile, in particular tile IR, what the programming model looks like. We can touch a little bit on GEM and extending the CUDA platform. We'll touch a little on tile gym and some performance analysis, and then do next steps. Okay, so let's talk a little bit about the programming model. So, historically we've had kind of two major approaches. The first was the spread level model that we see in CUDA, where the user is responsible for defining a kernel. They split work into blocks, divide data. If you need to do tiling, you're doing it on your own, and then maps all of that onto the resources available. As time has progressed, we've developed a number of libraries that build on top of this to provide some capability where you end up just calling a library function using a standardized API like BLAS or something like that to implement your operations. And so that was meant to be very high level for the type of work that is commonly seen across applications that need to be accelerated. This is commonly the case for scientific applications. But really what we're seeing now is that there's a need for a middle ground where maybe CUDA on its own is a little too steep of a hurdle to get over, but there are not library solutions that solve a particular problem. And so a middle ground and maybe an easier access point for accelerated compute is something at what we're calling the tile level. And to be clear, this is not really NVIDIA's invention in terms of programming language. This was all started with the Triton language that I believe came out of OpenAI by Philippe Tillet. And you can follow this link below to see what that looks like. Many of you have probably used Triton and seen some of the benefits. I know in work that I've done with other national labs, particularly for Python applications, Triton has been a really interesting tool for getting onto the GPU. It's been very performant and it has some additional capabilities that we haven't exposed in a CUDA-based programming language prior to today. But the takeaway is that we see this need, we see it being developed elsewhere. Our hardware supports this, but we haven't exposed it to the user through a programming model that is part of the CUDA ecosystem up until now. And so this is kind of the foray into doing this tile level programming model that looks somewhat similar to Triton, but as you'll see in subsequent slides, we're expanding the ecosystem that it applies to as well. So the idea here is that the user is responsible for splitting work into blocks and divides data into tiles, but the system is responsible for mapping those onto the resources that are available. So in practice, this is a simplification of the programming model. It allows you to do kind of the minimal subset of what is required to divide your problem up into work, and then let the system handle spreading that work across the compute resources. This has a few advantages. One, it's simpler for the user to design, but in addition, we now have an extra layer of flexibility in how this is mapped to hardware. And we can do that with the hardware that you have in mind in particular. So what we're targeting is an intermediate representation that we're now exposing as something alongside PTX. If you're not familiar with PTX, it's kind of a high-level instruction set for CUDA devices that is portable across generations. So Tile IR is analogous to that, but really for the tensor cores in a GPU, which incidentally are one of the largest sources of compute capability in an NVIDIA GPU. Okay, so for for the programming model, so we've got a grid level model that we see with cuBLAS, for example. We've got the thread level model that we see with CUDA. For tile level, up until now, there's not been something that NVIDIA has provided directly that enables this. There has been intermediate representation that is targetable by other programming languages, which is why Triton has been able to exist. But from a CUDA environment perspective, this is the first foray into this. So this is where CUDA tile fits in. It's kind of this intermediate um, uh, capability that is now exposed to make development simpler while still getting the performance that we would see on a speed of light implementation with CUDA. Okay. So, the question is, why do we want to evolve again? This is a pretty major departure in how uh, we've branded CUDA up until now. In fact, this is arguably the largest release or largest change to the CUDA ecosystem effectively since CUDA has started, right? So we've had, the addition of libraries that build on top of CUDA, but there's not been a fundamentally new programming model within the context of CUDA since CUDA itself. But the idea here is that we want to simplify performant GPU programming for data parallel applications. And we see a lot of that, right? So this is particularly common in the AI world. PyTorch is effectively what we're seeing lots of adoption on, and it's why Triton ended up being as popular as it is. These are common paradigms for applications that use accelerators. We're also trying to target from any language. Python is obviously a high priority, and that's what I'm going to talk about most today. But the idea is that we really want this to be something that can be done across languages. And so I'll touch more on that later, but we really want this to be an ecosystem, a language ecosystem-wide capability. And in the context for that, what we're exposing right now is something called Tile IR AS, for Tile Intermediate Representation Assembler, that other languages can target. And we've got a few examples of that already. So Python is, where we've kind of landed as an initial effort. C++ is next, and I've seen internally that we have the capability of using Tile IR from C++, but there are other languages that will come as well. And by nature of this project being open source, other language developers can bring in Tile IR to their language as well. And then finally, we really wanted to define a stable abstraction for tensor cores and related hardware. Again, so I mentioned that the tensor cores on an NVIDIA GPU are realistically the most powerful or most capable compute portion of the GPU. And you can see with the diagrams that I'm showing behind these 3 points, how this has expanded over time. So with Volta, we had a relatively small tensor core, that was, an acceleration method for, in particular, matrix multiplication. But you can really think of these as fundamentally kind of systolic arrays, right? These are similar to what we see on other large-scale tensor devices. NVIDIA has just exposed it as part of a broader hardware ecosystem on the GPU. But you can see that they've gotten substantially larger over time. And this just goes up to Hopper. We're already on Blackwell. Sorry. Why did that change? Okay. There we go. You can see, we go up to Hopper on this case, but Blackwell, expands this even further with the next generation. And then for the next system that NERSC is getting, Doudna will have a generation after that even. So these tensor cores are getting more and more powerful, and this is a mechanism for us to expose them directly to a user as a mechanism for getting high performance code on the GPU. So what do we actually abstract? So in the context of CUDA SIMT, single instruction, multiple thread, the unit of execution is a thread. So you write functions that are executed by many threads at once, and we call these kernels. The set of threads that an SMT kernel runs on is called a grid, and it's hierarchical. It's organized into different subgroups of threads, warps of threads, blocks of warps, and clusters of blocks. So users define the shape of this hierarchy, and that's what we're seeing here in this diagram is that these are all user-defined parameters, but they are exposed as a hierarchy that allow the user to target the hardware. For tile IR, the unit of execution, the unit of execution is a block. And a block is a group of threads or execution resources that has a single thread of control. So this is a little bit different than SIMT. We have one execution thread and control, and you write tile kernels that are executed by many blocks at once. But each block only executes the kernel once on the control thread. Okay. So this is a little bit different than what we've had in CUDA previously. For data, the unit of data under single instruction multiple thread is an element. So if we've got an array, we're iterating over the elements of that array. You would write scalar operations that operate on the elements of each thread, and you want each thread to apply an operation to multiple elements. Then you write a loop. There's no native array operation in CUDA SIMT. For tile, this is a little bit different. Everything is effectively expressed as an array. You express block-wide operations on entire arrays. And we'll get into what the syntax of this looks like in a bit. But the idea here is that, this is a fundamentally different programming environment. Okay. So in both SIMT and tile programming, the user is responsible for splitting the computational work into blocks and dividing the data into tiles. But the key difference here is that between SIMT and tile, who is responsible for mapping blocks and tiles onto the execution resources and memory. So once you partition your work and data exposing parallelism, there are still decisions to be made. What elements of data will each thread work on, for example? You also have questions of where does each thread keep copies of those elements? And we have questions of how should these local copies be laid out in memory? So for SIMT, all of this is something that the user is responsible for. And this includes actually going back to global memory, for example. And then there's the question of how we actually map these operations to computations that the hardware supports, right? So that is going to be dependent on the architecture that we're operating on. The generation of the NVIDIA GPU, for example. We're seeing in the middle here, we've got multiple generations of tensor cores, and in programming this with CUDA directly means being aware of what what the capabilities of these individual hardware's generations are and accounting for them to optimize that pattern. So for CUDA SIMT, the user's responsibility is basically all of this. You're responsible for splitting work into blocks and dividing the data into tiles and mapping blocks and tiles onto those threads. You're responsible for figuring out a memory movement strategy. You're responsible for a compute strategy. If you're using tiles, you need to be responsible for what the memory layout of those tiles looks like, as well as storage and interactions with shared memory, for example. So really, this is you can think of CUDA as basically the the you know the system doesn't provide you any guidance. You are responsible for doing it all, for answering all of these questions. There are many tools available to help you make these decisions, and we can help after the fact, once you've made a decision, tell you whether or not that was a good decision. That can be done with insight tools, for example. But it's still up to you to implement the best solution if you want to get there. For tile IR, a lot of this becomes the system's responsibility. And so this is where it becomes a simplification for the user. So we split work into blocks and divide the data into tiles. That is still a user responsibility, in part because it's very difficult for the system to understand your goals with your application. But once you've done that, once you've split the work into blocks and divided data into tiles, there's a lot that the system can do for you if it knows enough about the hardware that you're trying to operate on, as well as what you've done so far to split the work into blocks and divide it into tiles. So that means in practice that we can have the system be responsible for memory movement and compute and tile memory layout and tile storage, and actually mapping the blocks and tiles onto threads. And all we have to do that is explicit is parallelize by dividing the problem up into blocks and tiles. So within each block, everything is single threaded and you just perform array operations on those tiles. So this gets into, what does this actually look like in practice? So CUDA Tile IR is a new instruction set for NVIDIA GPUs. It's an abstract machine model for GPUs. So what that means in practice is that, it does not have you are no longer responsible for targeting the hardware specifics of the GPU that you intend on operating on. That is portable, and in fact it's compiled, or it's just in time compiled for the hardware environment that you're on. So we can express any program operating on regular arrays or data parallel problems in this instruction set. And as a result of this instruction set being a virtual instruction set that works across generations of NVIDIA GPUs, it's easier to achieve peak performance, in part because what's going on under the hood is the system is making decisions based on that hardware, whereas you might not always do that in CUDA, right? You might, in order to achieve that on your own with CUDA, you'd likely be generating generationally specific kernels for your problem. In this case, since a lot of the work that is going to be specific to a GPU generation is handled under the hood, we can do that at runtime or through a just-in-time compile step that enables us to optimize for that particular hardware then and there. It also provides a stable and portable way to program tensor cores and other GPU coprocessors should we go that direction. And we've really positioned it as something analogous to PTX. So I mentioned that earlier. It's just another part of CUDA. The instruction set, PTX again is kind of a virtual instruction set, but a little bit less system controlled, I would say. So the idea here, though, is that it fits into the rest of the CUDA ecosystem, and it's just another part of the CUDA ecosystem. So the graph here I'm showing on the left shows, maybe a future path, or in some cases, current path. With Cutlass, I think we're starting to build on top of Qtile as well, where we can build on top of these now multiple paths to getting to a GPU executable. And in practice, there are some cases where the library that you end up using may switch under the hood how it actually implements its operations on GPU by switching from CUDA to Qtile. For example, I'm showing here Cutlass is built on top now of both CUDA C++ and Python and Qtile. As time goes on, we expect that even us at NVIDIA will be developing on top of Qtile more and more because it's so easy, relatively speaking, to get good performance. And we can talk a little bit about that in future slides, what that actually looks like. But the takeaway from this is that you may already use something like TensorRT or PyTorch or JAX. Those in turn are going to be built on top of libraries that we provide either through cuDNN or cuBLAS. And in turn, those may be built on low-level primitives like Cutlass that are in turn implemented in now Qtile. So there may be changes under the hood that get better performance for the framework you're using as a function of Qtile existing and being usable, even though you personally aren't writing in Qtile. So this is an example of doing a matrix multiplication between CUDA Python using the traditional CUDA SymT programming model and a Qtile programming model. So this is explicitly called out as a naive approach. This is, probably the n cubed approach of matrix multiplication. There are optimizations that we can do against this, and I'll show that in the next slide. But this is if you've just learned matrix multiplication, you want to try it out on a GPU. You know a little bit of CUDA. This is maybe something similar to what you would end up implementing. Is this relatively naive approach that is the triply nested n cubed matrix operation. And in Qtile, this is how you would implement it on the right. So you see that we're defining um, I forget the term now, the Python decorator, I think is the term I'm looking for, on our matmul function that basically says that this is a Qtile kernel. So this is all that we really have to do. There's a calling function that's not shown here, but we're also not showing that in the CUDA Python implementation. And really we're just taking in 3 arrays and a shape. We're doing the memory operations to come up with a sum and grabbing tiles out of the arrays and doing an operation on that and then storing it back into our resulting array C. And we're doing something very similar in the CUDA implementation. But as a function of this happening in a tile programming framework, a lot of the optimizations that would happen for a matrix multiplication operation are going to happen implicitly as part of this Qtile implementation. And I'll show you what this looks like in this slide. So this is the effectively speed of light non-portable CUDA C++ implementation using SymT. So this is C++ CUDA. It's this is an eye chart certainly, and I think unless you've got a large display, you're probably not reading this line by line. But the takeaway I think of this is that these are similar in capabilities, but the one on the left is much more verbose, requires much more expertise to develop, and yet we're going to end up with a similar level of performance out of this. I'm going to touch a little bit on the intermediate representation memory model, and then we can dive into some other examples, and I'll show some performance results on a few operations implemented in CUDA. So, tile has a formally defined memory consistency model, and that is important for applications to be aware of. We talked a little bit about, some of the implications of memory operations in the C++ conversation yesterday. Similarly, for this, in order to implement arbitrary algorithms, we need the ability to express memory operations that are, sometimes ordered, or maybe for our operations, we don't care. So tile IR takes the assumption that memory operations can be unordered under most use cases, but they expose a capability of ordering them using these TKO operations for token ordered. So like I said, by default, memory operations are unordered, but if we absolutely need them to be, then we can do these TKO operations. So what this means in practice is that for any pair of memory operations, the order is undefined. And in tile IR, you can use tokens to order them as necessary. And some of this will happen on your behalf behind the scenes. This is in the context of the intermediate representation. So what we're seeing with the Python implementation is the high level language specification. What that gets compiled to is the intermediate representation, and some of these will be exposed. And so the takeaway is that you probably don't need to know about this under most use cases, but it's good to know that this exists in case you run into situations where what the system does by default is not what you're expecting. All right. Front ends handle token passing, and we'll see. I think I have an example in this slide deck of doing this, but there's a broader slide deck that I can potentially share that has examples of doing this in Python, C++, and Rust today. And then there's the specification has more details on how this is actually implemented. Okay, so in Qtile, this is a front end to the Qtile IR interface that I'm talking about. So it's clear to delineate here. So I'm covering multiple kind of related topics simultaneously, and I'll make a point to differentiate that right now. So Qtile is the Python interface for the assembler that generates tile IR, which is CUDA tile. And so there's a Python interface that is relatively simple to use, and that's what you're seeing here. That's implementing a softmax operation, but under the hood, this is being used with an assembler to generate CUDA, or I guess tile IR code that will run on the GPU. So it exposes CUDA tile as a NumPy-like array programming model. And really, this is yet another layer of abstraction that allows you to avoid some of the complexities that are necessary for the tile IR interface that we're talking about in a Python interface. So this is, a layer simplified from the intermediate representation. But you can think of this as where you want to program, right? And programming languages like Rust and C++ are going to have similar capabilities where a lot of this is abstracted away from you, and you don't have to think about the intermediate representation any more than you do in C++ for CPUs, for example. So this example is implementing a softmax across my I array. And you can see some of the operations that are defined here and how they're implemented. So As an example, just to get CUDA tile in your Python application in the first place, we do this import CUDA tile as CT. Let me bring up my laser pointer so you guys can see what I'm pointing at. So this is kind of, the initial, bring CUDA tile in to Python. We defined a function which is something that is going to actually operate on the GPU. We can also define a kernel, which is analogous to the kernel that you would see in C++, CUDA, that is kind of the entry point for the GPU or for your application to run something on the GPU. And you can kind of see the structure of what we end up doing in a Qtile application. So we'll load tiles. These are local to this thread, and they're going to have some shape associated with them. In this case, they're one-dimensional, and we're going to load uh, based on the index, the block ID, and then for each one of those, in this case, we're going to do a max reduction. And there's some, parameters to reductions on how we want to um, actually have them implemented, right? So we're going to do this. We're going to do a max reduction on C. We're going to take axis 0, which is the dimension that we're operating on. Since it's a one-dimensional array, we're just doing it on the first. We're keeping dimensions, which means that we're not reducing the dimensionality of the outputting array. So max will have the same shape as C. And will not reduce the shape of it. Num is doing the exponent, and here we're not keeping the dimensions, so I believe this will reduce down to a scalar value in this case, since it's a one-dimensional array being reduced, and we're not keeping the dimensions. So this is the numerator. Denominator, we're going to keep the dimensions as well. And then finally, S max is going to be our softmax value. We're going to take the numerator and divide it by the denominator, which is going to produce yet another one-dimensional array. And now we can store that back into our output, Smax. And we're going to store it, we'll store it back into global memory. Um, so another kind of I guess what I'm trying to see what so this is the same capability, I think, right? So that's a redundant slide. But some information to share here is that global arrays are mutable and accessible by all logical blocks, right? So that is what the read operations are doing. So we're loading into C that and in theory, you could do other block IDs or different ranges if you wanted. The store operation is also storing into global memory. And then what the launch actually looks like. So this is calling that capability. So we've got now our device function here. So this is the previous slide. The section in green is what we've previously been discussing in the past couple slides, but we've added now how to actually launch this. So we're creating a CUDA device I. We're going to do randomly generated. We're going to do output, which is going to be device array like I, so it's going to have the same shape and dimensions. And then we'll actually launch the CUDA tile kernel, our function, I guess. So we're launching the softmax function. We're specifying a grid size and the parameters, and then the shape, or R, I guess, in this case. And then once we've launched that, we can get the result back. So this looks kind of similar to what you would expect doing CUDA generally, except that the operations here are now at a tile level rather than at a thread level. So that's a redundant slide. Sorry about that. Um, so the kernels are launched with the same underlying APIs as SIMT kernels. And what that means in practice is that, this is using a lot of the same mechanisms that you previously would use with, say, CUDA for Python or CUDA C++. And so a lot of the same mechanisms are used. We're not reinventing the wheel everywhere here. It's going to be syntactically similar to what you've come to expect out of CUDA. And as a consequence of that, it's interoperable with other CUDA code, right? So you can do a traditional CUDA kernel. Here we've defined just-in-time compiled vector add operation alongside a CUDA tile function. These can coexist in the application and even in the same source file, and you can launch them on the same stream. So interoperable if you want to operate in CUDA in some cases and CUDA tile in others. That's completely doable across languages even. So I mentioned earlier that I wanted to touch a little bit on performance because I think that, really is, a critical component of this, right? That's why we're all trying to use accelerators in the first place is to get good performance. And so this is, to justify that CUDA tile actually is performance, right? So we have a few examples here running on a Blackwell system, B200 GPU. And we're comparing a few, I guess we'll say AI-inspired operations. So we've got a GEM FP16 operation, fast multi-headed attention at FP16, um, with a couple different options here. It produced functionally the same results, so we won't dive too much into the differences there. And then a decode operation. And you can see that, in two of these actually we're coming out ahead at slightly a bit above 1x the baseline state-of-the-art implementation in CUDA by just using Qtile. That's not going to be universally true. So for the FMHA operations, you see we're getting pretty close, but not quite the same level of capability. But again, to go back to one of the previous slides that I showed, the difference in code between these two for each one of these implementations is pretty massive. And more to the point, the implementation that one would come up with under Qtile is much more likely to be close to this versus what a novice CUDA programmer would come up with under traditional CUDA. So, these are state-of-the-art capabilities for the CUDA implementations. And then these are, first pass roughly of a CUDA tile implementation. Presumably, there's some expert who has implemented these and knows what they're doing, but the implementation details are pretty, these are not complicated implementations, I guess is what I'm trying to say. They're comparable to what a novice might write. So I mentioned that there's going to be a broader language ecosystem of support for Qtile. And so, really this is a set of languages that we're going to expose this with. So Qtile is out now for Python, and it's released as part of CUDA 13.1. But there are more languages to come. I mentioned, C++ is something that we're working on. We'll probably talk more about that at GTC. We'll also talk about this in the context of Rust and um, and and that will be open source as well. And we expect more languages to be easily able to adopt Tile for their native kernel authoring already. just looking cursory this morning at what the tile IR ecosystem actually looked like. I'm pretty sure I saw a Julia implementation. So you can see that the consequence of this being open source and flexible in terms of an intermediate representation means that there's already a community around this that is building more capabilities than even we're dedicating our time to at NVIDIA. But you can expect that this will be a growing ecosystem. And the fact that we can get performant code out of uh, reduced user involvement is pretty appealing across languages. Um, let's see. So I'll touch a little bit on an example of this, what this looks like in C++. There's a new kind of keyword in C++, tile global, that represents the descriptor for a kernel. But other than that, it looks, fairly similar to what you'd expect with a CUDA application, right? So we're defining a kernel and its parameters. This looks like fairly modern C++ with auto everywhere. We're using CUDA tile partition views to get, basically the block based on the index. So this you can think of this as basically the C++ analog to what we were doing in Python. And this is just to show that, this is already there, right? We're already doing something like this for C++, and hopefully this will be pretty appealing for the C++ community as well. So it's a similar level of abstraction, and the kernel structure is nearly identical. For Rust, this looks pretty similar. I'm not a Rust programmer myself, so aside from the fact that I know that this works, I can't tell you much about what this actually looks like. If anyone has comments on it, I'm happy to hear them and see what you think of this. But just to know that this is coming as well for Rust. Um, so exporting the CUDA tile intermediate representation, this is something that is, I think, pretty interesting as well. It's a capability that is provided. So the idea here is that you can use the intermediate representation to generate code and then share that and include it with your executable, for example, right? So this is analogous to what we've done historically with CUDA, but there are some interesting capabilities that come from this, and that you can program tile IR in one language and use it from another, and that's something that you could hack your way through with CUDA as well. But it's pretty noteworthy that you could actually do your development of high performance kernels in Python and then use them in a C++ application, for example. This can be included in your FATBin files and then launched from a driver from any language that's capable of launching GPU kernels. And the nice thing about this is that, since it's still the intermediate representation bytecode, that this can be portable to future generation of GPUs without having to recompile. You're storing the intermediate representation, not the compiled code. I'll touch a little bit on something that we're calling Tile Gym. This is a collection of kernel tutorials and examples for tile-based GPU programming. This is available today on GitHub. You can go take a look at NVIDIA Tile Gym, and it's the home of Qtile examples and integrations. So it contains an initial auto tuner, which is meant to help you get performance out of your kernels. The whole point of this is to make getting good performant code available to a broader audience, and this auto tuner is one additional capability that provides a mechanism for doing that. It's an initial auto tuner is part of the GitHub repository, I believe, and it has an official API that will land in a future release. So I want to touch a little bit on what our roadmap looks like. So part of why the demo that I'm going to show after this is just a demo rather than an interactive session where we can walk through actually doing this is that the current requirements for Qtile are somewhat constrained. So first of all, it requires CUDA 13.1, that is, or higher. That's probably not long term a hard constraint to meet. But I think, I'm not sure if Perlmutter actually has 13.1 on it yet. I'm pretty sure the answer is no. And so that is a complication. On top of that, we also require a fairly recent driver, I believe a 580 driver, to expose the underlying capabilities on the GPU. Uh, and then finally, right now, this is limited to Blackwell and later generation GPUs. I'll touch a little bit on that on a future slide, I think. But yeah, that's the constraints here are relatively tight, and so we'll do a demo rather than an interactive session. If you do happen to have a system that meets the criteria, you can find examples on GitHub, and I'll point to those at the end of the slide deck. But just to talk a little bit about what our roadmap looks like. So we require Blackwell right now, but other families to follow. There's just-in-time compilation and offline compilation supported right now. Support standard data types. CUDA forward and minor version compatibility is included already. There's some semi-formal specification of the immediate representation, and we're working closely with the broader public development around MLIR as a dialect. It does support both Windows and Linux right now, and so that's all under Tile IR. Qtile, the Python package, is pip installable now, and that's exactly what I did to go through the demo that I'll showcase in a few minutes. The API is NumPy-like, as you saw earlier, and it supports some integration with existing frameworks and is open source on GitHub. Um, Longer term, our roadmap has a number of probably notable elements here. The second one is probably the most notable for Perlmutter users is that we're expanding the GPU family to support Ampere and above. So that will include the A100s that are on Perlmutter. That once that support is added, which is going to come in a future probably CUDA 13 release, Ampere will be supported for Qtile, and we can do this on Perlmutter, provided that the driver and CUDA installation are up to the standard that's required, which is an easier lift than replacing all the GPUs. Um, the obviously the roadmap will include performance improvements, and function level interoperability for calling into existing code. We're going to get better tooling around this, of course. This is basically a minimum viable product or MVP release of what can be done with Tile IR and Qtile. So think of this as an initial release. Things will get better from here, but I think hopefully if you're able to develop it and already you find it to be a pretty reasonable experience. Um, okay. Next steps. So there's some information here on how to get started. There's a documentation page that is on our developer hub. I'll share a link. So the link will be in the slides that we share. I can also share it separately on the document that we're sharing. Qtile can be directly installed from PyPy using pip. You can take a look at the code on GitHub. You can look at the MLIR dialects on GitHub as well. I guess one of the takeaways here is that we were really after friendly testers of this. This is a public release, but it's the first release so far, right? And so hopefully, if you find this interesting and you have ability to run these examples, we'd love to have your feedback. We'd like to understand where where you find it useful, where things fall over, and go from there. I also have a link here to a quick demo video on YouTube that I based my demo on that I'm going to showcase. And I think it's a really good introduction to, kind of going from, I have the hardware required, I have a Linux installation with a CUDA driver. How do I actually get started with CUDA tile on Python? And it's a pretty straightforward process. And this video walks you through it and gets you up and running with a simple Python application that does some computation with Qtile. And I think that's it for my presentation. So the rest of the time I wanted to dedicate to a demonstration. Um, so we've got probably about 35 minutes left. I don't think I'm going to use quite all of that time, but I will dive into a demo. Okay, so first of all, before we move on, are there any questions? Anything I covered there that is an outstanding question?
There are a few questions, Scott, if you can hop over to the
Sure.
document.
Let's bring up the document. I don't think I actually had that open. Maybe while I'm bringing this up, Vinny, can you just share one, or maybe whoever asked one can go ahead and just ask it out loud.
Um, yeah, one question is asking in the uniform launch API example, can the grid size be inferred from the function parameter and data shape? Um,
Yes, I believe so. So let me go back to the presentation. So you should be seeing my screen now. Um,
yes.
so uniform launch APIs. Yeah, okay. So the question is, can this launch configuration be inferred rather than being explicit here? That's a good question. I actually don't know the answer to that. I think all the examples that I've seen have this explicit. So we're doing a grid size of 64 here. I think that the short answer is it probably could, but the math is going to be very similar to, what I'll showcase in the example where we're basically, taking the bounds of the arrays that are inputs and doing a sealing operation. In this case, it happens to be, the integer division works out exactly, so we don't have to do a sealing operation, but we're just doing a configuration of a grid size here. I think my understanding is right now that has to be explicit. It's possible in a future generation that that becomes implicit. All right, so I've got the document up. I apologize. That probably means that maybe I can move this over to this window, then I can go back to
Can
sharing.
read another question to you. Could you comment on the CUDA support for FP64? Because lots of scientific simulations require
Yeah, my
FP64.
understanding is that yes, it's supported. So let's see, I think. So, we call it explicitly FP4 mixed precision support in our roadmap for Qtile. But I think, the more traditional floating point types, FP32, FP64, FP16 are supported from the get-go. Um, I can follow up on that to make sure, but I believe FP64 is supported here. The tensor cores in NVIDIA GPUs support FP64. One of the things that I think will be interesting to see is if we're able to use the FP64 emulation that is present in Blackwell and beyond using these operations. And I don't know the answer to that, but I would expect that if it's not already there, the near-term answer is yes.
Thank you. Another question is, are complex numbers and operations supported?
Um, that's a good question as well. I don't know the answer to that off the top of my head. I can follow up and see if the answer is yes or no, but I don't know off the top of my head. All right. So looking through questions. So will there be backwards compatibility? It looks like Vineeth answered that, but yes, the answer is yeah. It'll go back to at least Ampere, which includes the GPUs on Perlmutter. I think part of the so there's two parts to that question is will it be supported and will it be performance? I think right now the implementation I believe there's an internal implementation that goes back to Ampere, but the performance is probably not at a level where we're comfortable exposing that to users, especially as you know users on, say, Perlmutter might use this as their first introduction to Qtile and see, relatively poor performance on that architecture when the architecture fundamentally wasn't designed for this. So the idea is, we want users to have a good, not only a good programming experience, but a good performance experience as well. And if the initial release would not support that, then we're going to avoid that. Um, Lovelace, yes, I think so. It'll be Ampere and above, and Lovelace is I believe that was the 80 SM86 generation, and so that's this should go back to SM70 and above, I guess, if you're gonna map it to SM architectures. So 7.0 and above, I believe. There may be complications with certain implementations, like I would expect the DGX Spark to implement this as well, but you can imagine maybe like Jetson devices that implement say something Ampere related may not be ideal for this use case. I don't know that to be true. I'm just speculating a little bit. So Alfred, GPU usually has two tiles. Not sure what you mean by two tiles. Um, Are you talking about, so Alfred, feel free to chime in on over voice if you want, but are you referring to like what we're doing with the reticle tiles on a GPU with Blackwell and Rubin?
Oh, I don't know too much about the GPU architectures, but I was told that, for example, some of the CUDA GPU has two tiles, and then
So
yeah,
so I think
go
that's an
ahead.
orthogonal concept to this. So in tile qtile, we're talking about tiles as a multi-dimensional subset of your data, right? And so it doesn't map directly to some hardware limitation of your GPU. So there's not two tiles that are going to be executed in the context of qtile. It'd be each SM within a GPU, which is order, on Ampere and later it's order hundreds of SMs. Each one of them has a tensor core that is capable of executing these operations. And those tensor cores vary in size in terms of generation, which is why that this is an abstract concept. But the short version of this is that there's not just two tiles that are going to be executed on a GPU simultaneously. That's a different
Thank you.
concept. All right. Uniform launch API. Okay, we talked a little bit about that one. Scientific simulations, FP64. I think okay, so Vineeth says FP64 is supported. Thank you, Vineeth. Complex numbers, I don't know for sure. We can look into that and follow up with this document. With the different language optimized implementations, is the available feature set any different? For example, a code base that already mixes in Python and C++ would be there any particular performance advantage to writing the kernel on one side over the other? So Python versus C++. I think the short answer is probably not. The maybe as like Python and C++ exist right now in the context of CUDA tile IR. There may be differences, but that is just a function of, us not having it fully released yet. I think you can expect long-term parity across languages. In fact, really what that boils down to is that there's a shared intermediate representation of features that are implemented on GPU. And then the question is, how do we expose those in the language that the user is actually implementing? I think that's relatively universal how that will be implemented. And so I would expect that, save for minor deviations in timing of features, we would expect feature parity across languages. All right. Looks like we've gone through the questions. Okay, so what I've got here is three tmux windows opening on the same node. You can see down in the bottom left, this is a GPU node. It's got two RTX Pro 6000 Blackwell GPUs. I'm only going to use one because these are relatively simple operations. And I have up top, this is just a set of Python applications and a Docker file. So the requirements are like I talked about previously. We need to do NVIDIA GPU, Blackwell or later right now, driver version 580 or later. So we see that we're meeting that right now. And then CUDA version 13.1 or later. So this is, we're all good on this, but since this is a shared resource, I didn't want to screw up the environment too much by installing random things. And so I basically just built this into a Docker container. I can quick show you what that looks like. It's really not complicated. All I'm doing is taking a development CUDA base image, and then installing Python, Python pip, and Python VM in it. Then I'm creating a virtual environment and installing CUDA tile, NumPy, and CuPy 13. So pretty straightforward container. Happy to share this with anyone who wants to do this on their own. I'm not sure that this is necessarily best practice. It's just what was convenient for me to get the requisite environment up and running. So what I'm going to do is go through three examples. So the first is vec-add, which is a very simple application. I'm going to close this temporarily so that we can see the full application. This is a really simple application, and in fact, it's kind of trivial from a comparison standpoint. What we're doing here, we've defined a function vec-add that takes in two parameters A and B and then adds them together. And what we're passing them is two NumPy randomly generated arrays. So we're going to add these together. You can see, so we're creating arrays of vector size We're defining a tile size. We don't need that right now. We're defining a grid size. We don't need that right now, but we'll use it later. So I could probably actually get rid of this line and this line. So this is kind of the minimal version here, right? So got a vector add function, and it does exactly the same thing as the resulting expected calculation. And then we're just asserting through NumPy that we expect that these two results are almost identical. By almost it, we mean like with the exception of bitwise precision that may come from different order of operations. For example, we expect these to be very close, but maybe not exact. Since this is implemented in both cases with NumPy, it should be exact, but as a testing harness, I want to use this for the GPU version. So, when we run this, I'll go over here. We'll do Python vec add, and you can see vector add example passed. So that assert was passed, and we present vector add example passed. So this is like trivial, right? We don't, no one would probably write code like this, but we were doing this as kind of a baseline for how to bring in Qtile. So I'm going to take a look at the first Qtile example. You can see this gets a little bit more complicated. I had to bring in ceiling, bringing in CuPy, as well as CUDA tile. CuPy just to showcase the ability to interop with another GPU offload package and use its data generation or having the arrays stored on GPU through some other paradigm is still completely fine here. So we'll touch a little bit on what this actually looks like in a second, but so we've got the kernel here. I'll walk through that in a second. I want to show a little bit more about what we're doing here under the kind of test harness to showcase how we're actually going to interact with this. So again, we've got a vector size. Now I'm actually going to use this tile size, and we're going to use that to calculate a grid. Similar to a question that came up earlier on defining what this grid looks like. In this case, just to make sure that I can handle arbitrary or nearly arbitrary sizes for vector and tile size, I'm doing a ceiling operation on the first dimension. So this is still going to be a one-dimensional operation, and then we're going to use CuPy random generation instead of NumPy for A and B. We're going to say C is a zeros array that has the same shape as A or B, and then we'll launch this kernel on the current stream. This might be optional, whether or not we have to specify the current stream. We do need to specify the grid, the operation that we're doing, and then a set of parameters, so A, B, C, and the tile size. And then once we're done with that, we'll copy A, B, and C as NumPy arrays back to the host. And we expect to get a result that is equivalent to the NumPy arrays A and B added together. And then again, we'll use NumPy testing assert array almost equal to compare C to the expected value. So that's kind of the testing harness. Let's take a look at the kernel and how that differs from what we saw previously. So the implementation with NumPy was very straightforward. It was one line. This gets a little bit more complicated. We need to get a block ID that we're going to use in subsequent loads to get the region of the array that this instance is going to operate on, and then we'll use that using Qtile load. We're going to load from A. We're going to use PID as the index, and the shape that we're going to get is a one-dimensional element or a subset of tile size length. We'll do the same for B. and then we'll do a result operation that is just A plus B. So this is, the functional equivalent to the one line that existed in the previous implementation. We actually get the calculation done here, and now we have to store the result back. So result is local, and it's not a global array, and as such, we need to use that as the data that we're going to store back into our global array, and that's what this operation does. So ct dot store, so qtile store, we're going to store into C. We're going to start at index or tile index PID, and the tile that we're going to save there is stored in result. Okay. Any questions on what this looks like so far? All right. If not, let's actually run this. So instead of vec_add, we're going to do qtile. And you can see that this ran. I'm going to bring back my NVIDIA SMI so I can take a look at what the GPUs are doing. Okay, so now I'm watching what my GPUs are doing, and as you can see, so briefly we spike on GPU 0, but it's not really putting a huge demand on this. And this is 2 to the 22nd size vector, which is I guess what um, it's a relatively small array, especially given the size of this. And so what I want to do in the last example is a two-dimensional version of this. And I want to showcase how relatively straightforward it is to take something like that one-dimensional and implement a two-dimensional version of it. Okay, so relative changes here. So now instead of a PID that is, or a block ID that is one-dimensional, you can get a two-dimensional block, and I'll save those into PID X and PID Y, and we get them from the block IDs at index 0 and 1. Now I'm passing a multi-dimensional tile index for both A and B, and I'm specifying a uniform shape, a square shape of tile size by tile size in this. Other than that and the store operation, this looks, functionally identical, right? So we've got a result that is A tile plus B tile. We're storing it back into C. We're now specifying a two-dimensional tile index, but the tile result is the same. So now in the actual harness for this, we can take a look at what differences exist there. I've changed the vector size on this is one dimension of this this matrix that I'm summing element or summing element wise. My tile size is still a square subset of that. My grid is now has 2 dimensions. Technically, it's always had 3 dimensions, but previously the second dimension was just 1. So it was this ceiling operation of vector size divided by tile size by 1 by 1. Now it's that ceiling vector size over tile size by the same in the second dimension. And then for generating the arrays, now I'm doing a 2-dimensional vector size generation for both. And then C is again CP zeros like A, so it's going to have the same shape as A. And this looks identical, this line, the launch kernel. So we're still launching on the current stream. We passed in grid, which is now it has a different shape. It's not some integer number by 1 by 1. It's same integer number by the same integer number by 1. So now we have an actual two-dimensional launch configuration here. The operation that we're doing is the same, vector add, except we defined it differently. And the parameters that we pass in are the same, except they have different shapes now. And the rest of this should be, the same as well, right? So we're copying it back as a NumPy array on the host for each one of these. We expect the operation to be the same as doing the NumPy operation element-wise sum, and we're doing a comparison against now two-dimensional arrays, and we'll see. One of the motivations to doing this was that we could give the GPU quite a bit more work. That kernel is very simple, but if we do a lot of it, we can see that we actually now hit the GPU somewhat hard, right? We've got briefly, we had a 13% load under NVIDIA SMI, and then the rest of it was just copying it back to the host and comparing it with a NumPy result. So it's still pretty fast, but this was just a showcase that you can take a one-dimensional example and fairly easily turn it into multi-dimensional. And I think that's really it that I wanted to show. Looks like there's probably some more questions in chat. Let's see. Are there any questions on the examples that I've shown? So Alfred has is the Qtile demo taken from the GitHub page? Not exactly. So there are some examples So yesterday I showcased the C++ std_par tutorial that came from the accelerated computing GitHub repository. There's also examples for Qtile under there as well. They're different than this, and so if you're interested in trying out some of the capabilities that Qtile provides, that's an excellent resource, and I'll make sure that that gets linked in to the document here as well. But it's a different set of examples. The example that I provided here today is based on that YouTube video that another NVIDIA employee put together to quickly showcase Qtile, and so I ran with it. I implemented the code he describes on with Qtile which is the one-dimensional code. It's functionally identical to the 1D implementation here. And then I expanded in either direction, how we would do this just as a starting point with NumPy, and then the two-dimensional version. So you should be able to you can look at that video and get the exact implementation that I started with. And I'm happy to, if you want to play with these yourselves, I'm happy to share these examples. They're kind of trivial, but showcase what's possible with Qtile. Let's see. There's another question with a different. Oh no, that's the one we already answered. Okay, so are there any other questions that you guys would like to talk about? We've got a few minutes left in the time we allotted for this, so I'm happy to answer questions. Feel free to just jump in. Yeah. Or if we want, we can give a few more minutes back. Alfred, it sounded like you looked like you were going to come off mute. So if you got another question, go for it.
What is the link to the YouTube video that you're talking about?
Oh, it's like 5 minutes. And that goes through, some of the installation of the package with pip, and then walking through the code example and then running it. So it's very short. And I'll share the link is in the slides that I'll share as soon as I'm done. But we can also put it in chat right away so that you guys can take a look at it as you see fit.
GitHub repo you showed yesterday about for the overall training tutorials exercises that we had std_par directory. There's also a Qtile directory there.
Yes. Yep.
And that overall link is in the Q&A doc under slides.
Yes. So the accelerated computing hub. So I can stop sharing this and then share a Firefox window where that is. Let's see. Share. think you should be seeing my Firefox window now. Is that correct?
Yes.
All right, so this is that main repository. So what we did yesterday came from this section. So this is the tutorials, standard parallelism, and then notebooks in C++, lab one. So this is what we went through yesterday. If you go back to the root of this, there is a set of tutorials, one of which is CUDA tile, and we've got some notebooks here, including an introduction to Qtile Python. So this is different than what I went through. It gets into some more of the features, but it breaks it down into steps, right? So kind of like what we did yesterday um, with C++ std_par, this would be an introduction notebook. Again, you're going to need the requisite hardware and software environment, which is why we didn't go through this today. But this would be if you want to learn more about how to actually use this, this would be a good starting point as well. All right. I see there's one more question. For instantiating the shape for CT load, does the tile have to be square dimensions? I don't think so. Let's see, do we have an example of that? I'm pretty sure the answer is no. There are some limitations on the shape, and those will be relaxed as time goes on. But I believe they do not have to be square. So the short answer is it's not arbitrary, but it also does not have to be square. So it's probably, some power of 2 in each dimension, or multiple of 2, some multiple of some multiple of 2, probably like, small. We did, a tile size of 2 to the 4, which is 16. That might be a lower bound. I don't know that off the top of my head, but while Vineeth is presenting next, I'll see if I can find any documentation on what the tile shape limitations are. All right, I think we've gone through all the questions. If there's any more, I'm happy to answer. Feel free to jump in, but I think that's all I wanted to present today. So I appreciate your guys' attention. Hopefully this has been useful.